Okay, great.
Okay, so hi everyone. My name is Zaire. I'm currently a PhD student at IRAP in France, and I've been developing this work with my collaborators. With my collaborators, my advisor and my advisor Jean-François, Thomas Gastine, Colin Fosson, and Julia Morin. So what can we learn about the magnetic morphology of full stars from numerical simulations? So let's start first with what we know from observations. So here I will show you the information that we have about the surface magnetism of stars. So in the y-axis, we have the luminosity, and in the x-axis, we have the effective temperature. And we have also some mass tracks here for masses with 0.8 to 1.2 solar masses. So here, each symbol corresponds to to a different star, and it contains information about the magnetism obtained at the surface of the stars using the Zeeman Doppler imaging technique. So here, the symbol is related to the surface strength, and the color is related to how much energy is stored in the colloidal field. So as the color gets more red, we have a totally colloidal energy. So we also have here, which is a little bit different from the previous representations showing the previous talks, the information about the axisymmetry shown as a tick outside these circles. So as the tick is totally to the left, we have this completely axisymmetric field. And as the tick rotates clockwise, getting totally to the right, we have this non-axisymmetric field. So as we can see, stars that lie above this dashed blue line, which are fully convective, tend to have a more strong fields that are axisymmetric and are more stored in the colloidal component. So as the radiative core develops in the stars, this field strength tends to decay, and it tends to increase the energy stored in the toroidal field, sometimes getting even dominant toroidal components. And we see also a change in the axisymmetry of the field when with the field starting to get more non-axisymmetric. So this evidences the impact of the internal structure in the field morphology. We can also look for M dwarfs now. Here in the y-axis, we have the mass of the star, and in the x-axis, we have the rotational period. And as we can see below this gray line, which represents the fully convective regime, we have these fully convective stars that tend to have more axisymmetric, strong fields, and colloidal more energy stored in the colloidal field. But as we move to these partially convective stars, we see that the field tends to get more complex, and we can also see that as the rotational period increases, the field strength tends to decay. So this shows some combined effect of convection and rotation in the field strength. So we can ask, is the magnetic morphology linked to a change at play in the stellar interior? We can see here the field strength with respect to the Rossby number. And I remind you that the Rossby number is the ratio between the inertia force divided by the Coriolis force. So as we can see here, I gathered this field strength derived from Zeeman Doppler imaging, and we can see young suns, star-like stars, and M dwarfs divided by fully convective and partially convective M dwarfs. And as we can see, we have two regimes here. We have this saturated regime for low Rossby numbers, where we have fast rotators, and we see that the field strength does not depend strongly on the Rossby number. It's more or less constant, the field strength. And we have also the second regime, which is the unsaturated regime, where we see that the field strength decays as the Rossby number increases. And by the way, M stars is around here. So we can see the influence of rotation in the magnetic field amplification. So how does the Rossby number connect with this magnetic field topology? So we're going to look now for numerical simulations. So I'm going to first define this quantity that's called dipolarity. So the dipolarity is defined as the energy in the axial dipole divided by the total energy in the modes up L equal 11. So we truncate our energy that we use to normalize because we want to compare these with observations. And as you can see here, I'm going to show you the results from a previous work of Gastine and collaborators in 2012. And you can see on the left simulations with a thick convective zone, and on the right, simulations with a thin convective zone. So if we first ignore the information about the symbols, we can see that we have strong dipoles existing at low Rossby numbers. And as the Rossby number increases, we see that we transit to more complex morphologies and no strong dipole is obtained after that. The same thing is also observed with the thin shell, but we see the transition, it depends a little bit on this size of the convective zone or in this aspect ratio. So if we now consider the information about the density contrast, which is defined as the ratio between the logarithm ratio about the density at the bottom and at the top of the convective zone, we can see with these bluish green symbols that when you have a weak contrast in the density, we tend to have this scenario occurring. So we have strong dipoles or low Rossby number, and as we increase Rossby number, we transit to a more complex morphology. But if we now look for the strongly stratified, these reddish symbols here, we see that even at low Rossby numbers, we don't get these strong dipolar solutions. So although we had very few simulations that could achieve strong dipoles in this low Rossby regime with high density contrast, which tend to be more realistic, as in stars we have higher density contrast than that. So if we now try to link observations and simulations, we have on the left the plot that I just showed you, and now here on the right I have the same stars, but now just a subset of it, which I could derive this quantity computed as we compute in the simulations. So I create here two categories that I will, that's based on this dipolarity quantity. We have dipolar, I will consider as dipolar surface fields, all the stars that have more than 25 of the magnetic energy stored in this axis, in this aligned dipole. And I will consider as multipolar all the stars that have less than that in the axial dipole. So as we can see, at low Rossby number, we can observe these strong dipoles here. And as we go to this high Rossby regime, we tend to have more complex morphologies. We also see that we have complex morphologies here at the low Rossby, and this was usually explained as the existence of bistability, where you vary the initial field strength and you could obtain different magnetic morphologies. And this was shown to behave like that also in simulations. But what is interesting here is that what we do not obtain in simulations is these strong dipolar solutions at high Rossby. So we are not sure what controls this magnetic morphology. Is that rotation? Is that internal structure? How is all that linked? So we wanted to investigate this with a numerical study. And the first thing we need to acknowledge is that we are still far from performing numerical simulations with realistic values found in stars. So for instance, stars have higher density contrast, higher forcing or vigor of convection, and also they tend to have a much lower viscosity than what we simulate. So we wanted to approach this with a parametric study to investigate the joint effect of rotation and internal structure on the magnetic morphology. And the second point, which is very important for our work, is that recent geodynamo simulations where the density contrast didn't exist showed that if the magnetic contribution in the momentum equation is strong, or if the Lorentz force is relevant in strong in the momentum equation, we have dipolar solutions existing at high Rossby number. So we wanted to explore this and question if we are preventing dipoles from existing with our choice of parameters. So we did numerical simulations of a thin convective shell, similar to what I show in the right when I showed Gastin and collaborators simulations. And we also investigate 3 different density contrasts, as you can see here. And we assumed moderate values of Ekman and Prandtl numbers that were also adopted, exactly the values adopted by Gastin and collaborators. But now what's different is that we used a different magnetic Prandtl number in order to get tuned a magnetic Prandtl number, which is defined as the viscosity divided by the magnetic diffusivity equal 5. That choice was not an arbitrary choice. It was based on scaling laws derived by Schreiner and collaborators in 2004, and it's highly dependent on the choice of Ekman Ekman and density contrast. So as you can, for these specific values that we used, the choice we found for the magnetic quantity number was 5. So let's first compare our results with the previous work in the literature of Gastini and collaborators. So here I show you in the y-axis the dipolarity. So I define the dipolarity here not as a fraction of energies, but a fraction of the field strength, but it's the same thing. As you are above 0.5, you have more than 25% of the energy stored in this aligned dipole. And as you are below, you have complex morphologies. So in gray, I showed my results, and in purple, I show the results of Gastini for this specific density contrast of 3.0. So we have higher magnetic quantity numbers than Gastini. They used 2, and we also explored larger Rayleigh number for vigor of convection in our simulations. And as a result, we got strong dipolar solutions for this higher stratification considered. So let's see how this appears in the Rossby number. So here you can see our simulations shown with different colors as the density contrast varies. In red, we have the weakest stratified case, and in blue, we have the highest stratified case. And as we can see, we have strong dipolar solutions for this low Rossby regime. And we also have these complex morphologies here, which are not related to bistability in our case, because we did not consider different fluid strength when initializing our simulations. It's also interesting that we obtained for the first time for these simulations with a strong density contrast, these strong dipolar solutions at high Rossby. And as you can see here in the surface maps, you can easily identify it. And we also saw a transition for more complex morphology at high Rossby number, as you can see here. So we want now to try to understand what is changing this magnetic morphology. So before we were looking for the Rossby number, which is the ratio between these first two terms, inertia and Coriolis. But now we want to look also for the other terms in this equation. So pressure, buoyancy, Lorentz, and viscous forces. So what I'm going to show you next is the relative importance of each of these forces, which are averaged in volume and time. So as simulation setup, and with the highest stratification, the density contrast that I used. So as you can see, each of the forces in different colors here that follow this color scale here. And we can also see the magnetic morphology, which for each run appears here as multipolar or dipolar. And as you can see, the first thing we can notice in this graph is that we have at first order a geostrophic balance. So we have this Coriolis shown in black and pressure shown in blue, balancing each other in first order. So the unbalanced part, which is the ageostrophic force that I defined as a difference between these two and is shown gray here in this graph, is balanced by Lorentz, which is shown in red, and buoyancy in green. And as you can see, sometimes inertia gets relevant and also starts to contribute in this balance. And it seems that the relative importance of inertia in the second order balance is responsible for controlling the magnetic morphology in these simulations. So as you can see here, for instance, we had one case that we didn't had a strong influence of Lorentz, but as soon as this Lorentz influence got strong, we had these dipolar solutions shown as circles. And as inertia was increasing its relative importance, we saw the transition here. So what I show you here is how this ratio was behaving for our simulations. So we can see that when Lorentz is much stronger than inertia, we have these strong dipolar solutions. And as inertia gets important in this second order balance, it transits to a more complex morphology. So it seems that when the Lorentz force is significant in the simulations, it's not only inertia divided by Coriolis that can capture this transition, but instead inertia divided by Lorentz. But the thing is, this proxy is not very convenient for observers. So we wanted to approximate this by the energy in the convective motions divided by the magnetic energy. So this is what we get for our simulations if we use this proxy based on the energy ratio. And we can see that this ratio between energy does a good job describing the magnetic morphology in our simulations. So we see that when the energy is in super equipartition, so the magnetic energy is much larger than the kinetic energy, we have these strong dipoles. And as the kinetic energy increases, we see a transition to a complex morphology. So we wonder whether this energy ratio was a universal mechanism valid for stars with different internal structures. So what we did, we computed the surface, and for the kinetic energy, we used the convective velocity from 1D models that were published in the literature for each of the stars. And for the photospheric density, we used some rough approximation based on the mass obtained, that we have strong dipoles lying here. And we also have this complex morphology. I remind you, it was only 40% of the convective zone that was convective. So what will better represent our simulations here was partially convective stars, as for instance the M dwarfs or these solar-like stars. But as we believe that this could be a more universal proxy, we also believe that these other stars could be better represented by this proxy. But this is a rough estimation, and we were happy to see that we indeed could capture this transition. So my takeaway message is we obtained for the first time strong dipolar configurations at high Rossby numbers and for a stratified system, and similar results were obtained before in the geodynamo context, but they did not consider this stratification in the convective zone. We also found that this ratio between inertia and Lorentz seems to describe the dipolar multipolar transition better than the Rossby number, and we proposed this kinetic divided by the magnetic energy as a more accessible proxy for the dipolar multipolar transition. So I thank you, and if you have any questions.
Thank you. So yeah, if anyone has any questions, then please raise your hand or say so in the chat. Yeah, Adam?
Hey, great talk. Just a really quick thing. Have you tried plotting this kinetic energy over magnetic energy proxy for the sun in your diagram and seeing if it lies in a weird part of the diagram? Because that's obviously something that people like Travis Metcalf would like to see.
Yeah, no, I didn't do that, but I will include this for sure. Yeah, I should do that.
Any more questions? Oh yeah, Julia.
Yeah, if I can comment on that, maybe on the place of the sun, the problem may be that if you consider it depends on how you consider the dipolar magnetic energy, and especially if you estimate it from the Zeeman Doppler map, which only considers the large scale field, you may be in a way biased in the sense that the magnetic energy in the large scale field for the sun is very low. It's only a very low fraction. So you can have the impression that it's dipole dominated, whereas it is debatable in the sense that the large scale component that you can observe with Zeeman Doppler imaging has some deep dipolar component, but it's actually energetically unimportant. So it may bias the conclusion you can derive from that.
Yeah, and it's definitely going to exist some difference here, because although in the fraction of dipole I truncate the energy for these modes up to 11, when we compute this ratio, this is not captured here. So yeah, we probably have this. I tried to look for different measurements for the magnetic energy to include this here, but it's very difficult since you expect, well, for several of these stars, if you measure several times the star, you have maybe some differences in the relative energy in this axial dipole, and we don't have not necessarily like works deriving the magnetic energy at the same time. So it was the best I could come up.
Okay, well, if there are no more questions, let's thank Bonnie again. Thank you.